I'm going to talk about the gyro average. If you come here to search for some Mediterranean food, I apologize, it's about plasma physics. So for a particle that's moving along the field line, it will, aside from the guiding center motion, which is along the field line, it will do a gyration around it, which can be expressed in this relatively general form. Sorry, I forgot why. So we could make some approximation to this process. Instead of calculating the whole real motion of the particle, which is really complicated, we could do some simplification in terms. Basically, we're just basically averaging out around the one cycle of a gyro motion. So say if I have a quantity, to be general, I would just make the quantity whichever quantity it is. We could do the Fourier decomposition to it. It will have an e to the negative I omega t, but it's not dependent on any spatial variable. So we just drop that. We can just add that in the future, if you may. So we transform the x space to k space, and we do the gyro averaging. Gyro averaging is pretty much the whole circle, the gyro motion. You can think of the gyro motion is like this. The whole circle. Do like a 2 pi circle, and you do the integral from 0 to 2 pi divided 1 over 2 pi. Since in this scenario, only the case k and big X is not theta dependent. Only rho is theta dependent. So we can pull out every other things, and then we're left with this, because k rho can be right in terms of k per rho s cosine theta. S stands for species. It's just a notation that I use. So if you didn't recognize, then you can check on Bessel function of first kind. The integral form will be written in such way. So for our case, the n equals to 0. So we ended up having a j naught k per rho s. So basically, exchange this thing with a j naught. So basically, Bessel function of first kind of zeros and one. So yeah, that's how we transform the real space to a gyro averaging to the guiding center space. So for similar idea, we could potentially have an average in a real space. So pretty much we did this is small x, by the way. So x minus rho, then they become a guiding center space, and then plus rho prime, and then back to the real space. So we wound up having a similar procedure, but we have instead of having x big X plus rho, we have small x minus rho plus rho. Then we have two integral from 0 to 2 pi in terms of theta and 0 to 2 pi in terms of theta prime. They're separable variables. You can think in that way. They're independent in a sense. So we do the same procedure as you can see. Then we have I k per rho s cosine theta minus cosine theta prime. So we do it 2 times effectively in terms of this, the Bessel function expression. Then we end up having j naught s squared. So we have we have expression pretty much gyro-averaging in real space. It's in the orange box. This is very, very important knowledge in terms. You will see that in my videos on the kinetic theory. It has very important implications of a kinetic theory. Basically, we can think for this quantity A, the amplitude of that will, for ion, will look like this, because, and the electron will look like this, because the gyro radius is ms v per over qsb. So the ion has much more mass than electron. So ion will vary faster than electrons, you can see. So the implication of that is for small k, which means the small wave number means a very relatively slow. So we have an adiabatic electron, and we call this region the ion scale. Then the ITGTM will be there. Ion temperature gradient mode and the trapped electron mode. For higher K will be in the electron scale. It will have adiabatic ion, since the ion cannot keep up with a fast moving. The electron cannot keep up with a fast moving particle. You can check that on the different videos that talk about the overview of micro instability.